Okay, so welcome to this next video in which we are discussing the GABA-A receptors and the benzodiazepine drugs. Okay, so we've seen that the benzodiazepines bind to a separate site on the GABA-A receptor. So we've seen that they bind to this benzodiazepine site here. And when you've got a benzodiazepine bound in the benzodiazepine site, what it will do is it will cause conformational changes in these these GABA binding sites on the GABA-A receptor. And now the affinity of this binding site for GABA, so how much GABA wants to bind in this GABA binding site, is going to increase basically. So GABA will bind here more readily basically. So that will mean that if we draw a little picture here, okay, so if we have our dendritic spine on our dendrite, so often what you have is axon terminals. They don't synapse directly onto the dendrite. Instead, the dendrite has little processes that come off it, known as dendritic spines. So this is a dendritic spine, and the axon terminals of the presynaptic neuron synapse onto the dendritic spines rather than directly onto the dendrite membrane here. Right, so basically, let's say that this presynaptic cell here is releasing GABA onto this dendritic spine. So it's an inhibitory synapse basically. So this neurotransmitter in here, this is Gamma-Aminobutyric acid. Okay, now there is more than just one GABA-A receptor on this postsynaptic membrane of the dendritic spine. So let's draw these multiple GABA-A receptors. So I won't draw them in any sort of detail, I'll just draw these little boxes to denote these GABA-A receptors here. Okay, so you've got a great number of them. Now, basically, when you release GABA into the synaptic cleft, not all of these GABA-A receptors are actually going to be bound to GABA. So not absolutely every single one is going to be bound to GABA. Now basically, if you put benzodiazepines into this synaptic cleft and allow the benzodiazepines to bind to these GABA-A receptors, then basically the fraction of GABA-A receptors which will now be bound to GABA, so we're going to leave the concentration of GABA in the synaptic cleft alone. That's exactly the same as in the initial experiment, but now in the presence of a benzodiazepine, the number of them which will bound GABA is going to be greater. So it increases the number that will actually be bound to GABA for a certain concentration of GABA in the synaptic cleft. Now, if you've got more bound to GABA, that means that more are going to be in the open conformation and allowing chloride anions into the cell. So the inhibitory postsynaptic potential that you produce, the size of the hyperpolarization of the membrane you produce, is going to be greater because you're going to allow in more chloride anions. Okay, so the inhibitory postsynaptic current is greater, so that leads to the inhibitory postsynaptic potential being greater, and that therefore has potentiated the GABAergic transmission. So it's made this neuron less likely to fire an action potential because the hyperpolarization has increased. This inhibitory effect has increased. Okay, right. So benzodiazepines therefore are going to decrease the number of neurons firing within the brain, okay, and this means that they can be used to prevent epilepsy and also as anxiolytics, very famously as anxiolytics. They can also be used to produce sedation, and actually another effect that they have is amnesia. Now this is quite interesting actually, because this is where it comes in that there are many different types of GABA-A receptors. So we've discussed that actually there are these many different types here. So some will have, for instance, alpha subunits that are alpha 1, and some will have alpha 2, alpha 3, etc. Now what you find is that different benzodiazepines have differing affinities for binding to different GABA-A receptors. And we can see that the benzodiazepine binding site is between this alpha subunit and this gamma subunit. So which alpha subunit you have seems to determine the affinity of the benzodiazepine to bind, and also the gamma will affect it as well. Now, these GABA-A receptors also have different physiological functions, so you'll find these at different points in different parts of the brain, and their role is therefore in the body and in the brain is different. Now, basically, the GABA-A receptors, which have either alpha-1 or alpha-5 subunits in, okay? So we've seen this main type here, this huge great type within the brain, this alpha-1, beta-2, gamma-2, this has an alpha-1 subunit in. Now basically, these seem to be involved in producing sedation, basically, and amnesia. So these seem to be involved in producing specifically amnesia. So basically what you find is that if you increase the activity of GABA-A receptors, specifically the GABA-A receptors with these alpha-1 or alpha-5 subunits within them, then you promote amnesia, okay? Now, instead, if you increase the activity of GABA-A receptors with alpha-2 or alpha-3 subunits in, so these other two that we saw, so this one here, this alpha-2, beta-3, gamma-2, this was an example of a GABA-A receptor which had the alpha-2 subunit in, and if you these other three here that we saw, they have alpha-3 in. So if you increase the activity of the GABA-A receptors with alpha-2 or alpha-3 subunits in, that seems to be involved in producing anxiolytic effects. Okay, so overall, we know that increasing GABAergic transmission not specifically any specific GABA-A receptors now, just increasing GABAergic transmission overall increases sedation, okay? It produces amnesia, which means loss of memory. Specifically, it produces anterograde amnesia. So I'll just make a comment for this. So it's specifically anterograde amnesia, which means it prevents the formation of new memories. So basically, if you give someone a benzodiazepine, and we'll see benzodiazepines that are very good at producing anterograde amnesia in a moment, if you give them a benzodiazepine, what it will do is it will increase GABAergic transmission, and if you increase GABAergic transmission for GABA-A receptors with these alpha-1 and alpha-5 subunits in, they seem to be involved in producing this anterograde amnesia. So the person will not remember what happened to them when you give them this drug. So if you bring someone in for, say, a minor surgical operation, what you often find is that if they're quite nervous about it, you may well give them a benzodiazepine, and it basically, firstly, it calms them down hugely. It's got very good sedative actions. And then also, they can't actually remember the surgical operation later on because the benzodiazepine produces anterograde amnesia, so that means it stops you laying down memories whilst you are taking it. So for that period when you're actually in the operating theatre, if you like, but it's a minor op, so in the surgery, let's say, then you won't actually be able to remember the operation because you weren't able to lay down memories. Okay, so it seems to be the alpha-1 and the alpha-5 subunit GABA-A receptors which are important in producing the amnesia effect, whereas the activation of GABA-A receptors containing the alpha-2 or alpha-3 subunits, so these two here, which contained alpha-2 and alpha-3, that seems to be important in the anxiolytic effect, so the calming down effect. Okay, right. So now, what we can say is that different benzodiazepines will have differing affinities for the different GABA-A receptors. So we've discussed that there are a huge number of different GABA-A receptors, and when you have benzodiazepine drugs that bind to this BZD site here, this benzodiazepine site, then the affinity of the benzodiazepine for that benzodiazepine site will depend on which alpha subunit and which gamma subunit you have here. So if you have an alpha-1 or an alpha-5 subunit here, the example of a benzodiazepine that seems to be particularly good at binding to those sorts of GABA-A receptors and therefore causing amnesia, and specifically anterograde amnesia, is a drug known as lorazepam. Okay, so lorazepam is a famous benzodiazepine, famous for producing amnesia. It's extremely good at producing anterograde amnesia, lorazepam. So all of the benzodiazepines have zepam at the end of their names. Okay, so just to summarize everything, lorazepam, it's a benzodiazepine, so it will bind to the benzodiazepine site on GABA-A receptors. Now, it's mildly selective for these GABA-A receptors involved in producing anterograde amnesia, so these ones with the alpha-1 or alpha-5 subunits in them. Okay, so it will bind to those preferentially over the other GABA-A receptors, and then what it will produce is it will increase the affinity of those GABA-A receptors for binding to GABA. So you'll have more GABA-A receptors bound to GABA, therefore more GABA-A receptors activated to open, and therefore a greater inhibitory postsynaptic current, and that will reduce the firing of neurons within the brain, and that seems to produce the anterograde amnesia. But lorazepam will also calm you down hugely as well, because it's not totally selective for these alpha-1 or alpha-5 subunits, and also the GABA-A receptors which have these alpha-1 or alpha-5 subunits, although we sort of categorize them like this as being involved in the amnesia, then they're not solely not involved in the calming or sedative action either. So this is a blunt categorization for something that won't be that blunt, basically. It won't be, and these ones produce amnesia and these ones produce anxiolysis. It simply doesn't work like that. But as a vague sort of good idea, then it's these ones that seem to be most strong in producing anterograde amnesia, and these ones that seem to be involved in the anxiolysis. And lorazepam seems to be selective for the ones that produce amnesia over the ones which produce anxiolytic effects. Right, now my second example of a benzodiazepine drug is the famous one, diazepam, known more commonly by its infamous brand name, Valium. Okay, so diazepam is the drug which is in Valium. Okay, so Valium is a famous anxiolytic. It's used to calm people down, basically, and as a sedative. Okay, so it's preferentially going to bind to these GABA-A receptors with the alpha-2 or alpha-3 subunits in, but again, it's not going to bind to these. It's going to prefer to bind to these ones, and that means that its effects, its anxiolytic effects are stronger than its amnesic effects. So lorazepam is better at producing anterograde amnesia than diazepam, and diazepam is slightly better at producing anxiolytic effects than lorazepam. Right, okay, but they will both overlap, basically. So diazepam will bind to these GABA-A receptors with these alpha-2 or alpha-3 subunits in, so these ones here, but of course we know it will be binding to this one as well. And it will bind to the benzodiazepine site between the alpha and the gamma subunit, and it will increase the affinity of the GABA binding site for GABA, so GABA will then bind, more GABA will bind to the GABA-A receptors, and you'll end up with a greater number of GABA-A receptors which have GABA bound to them, and that will increase the inhibitory postsynaptic current, and therefore you'll end up with lower levels of neuronal firing within the brain. Right, so those are my two examples of benzodiazepines, diazepam and lorazepam. Okay, I want to mention two other drugs. One which is an antagonist for the benzodiazepine site, and one which is actually an inverse agonist for the benzodiazepine site. So firstly, an antagonist for the benzodiazepine site, so I'll just write this here, a BZD antagonist, and I want to make sure that you know exactly what this is. So this drug is known as Flumazenil. Okay, Flumazenil. Okay, now Flumazenil is a drug which will bind to the benzodiazepine site here, but not change the conformation of the GABA-A binding site so that GABA has a greater affinity for binding there. So it's just a drug which will bind to this site and stop benzodiazepines binding, but it will have no effect on the receptor. So flumazenil is a drug that's important in people who have taken benzodiazepine overdoses, and it's important to say that benzodiazepines are dangerous drugs. If you overdose on them, they will kill you. They'll stop your brain from firing any action potentials at all, basically. Okay, so if someone has taken an overdose of benzodiazepines, the way that you would treat this is with flumazenil, which will bind to the benzodiazepine site, not do anything to the GABA-A receptors, so not increase GABAergic transmission at all, but simply stop the benzodiazepine drugs such as Diazepam or lorazepam from binding there. Okay, now let's talk about another, maybe a little bit more extreme drug, which is an inverse agonist. So this is always interesting. This is where terminology we don't often hear. Inverse agonist. So what is an inverse agonist? An inverse agonist is a real inhibitor, whereas an antagonist is, strictly speaking, what you would emphasize as a competitive antagonist. So strictly speaking, antagonist is something that binds to a site, such as the benzodiazepine site, and stops another drug from binding. Really, what you shouldn't actually have to put competitive antagonist, because that is the definition of antagonist. Nowadays, people often use antagonist just to mean inhibitor, but that's actually wrong, okay? And because people do use antagonist just to mean inhibitor, to stress the point that we mean a drug which binds to a site but does not stimulate the site, we now generally say competitive antagonist. But in the classical nomenclature, antagonist meant what we now mean by competitive antagonist. So really, I suppose I should put benzodiazepine competitive antagonist to be super clear. But when I say antagonist, that really, strictly speaking, should just mean competitive antagonist to you. Okay, but people do nowadays just use antagonist to mean anything which inhibits the function. Okay, so an inverse agonist then. The drug which I'm going to state as an inverse agonist is Rho 15 and then 4513. 4513. Rho 15, 4513. Okay, so this drug clearly is not used clinically. When you have drugs that are used clinically, they have more interesting names than that. Okay, but what this drug does is it binds to the benzodiazepine site, and unlike flumazenil, which was a drug which just bound there and did nothing and just stopped the benzodiazepine binding, Rho 154513 is going to do the exact opposite. It is going to cause a conformational change in the GABA-A receptor, and it's going to change the conformation of the GABA binding site here, such that the affinity of GABA to bind there is actually reduced. So basically, Rho 154513 does exactly the opposite of benzodiazepines. It binds to the same site, but instead of increasing the affinity of GABA to bind to the GABA binding site, it decreases the affinity. This means that if we go back to our picture down here, if we have fixed the amount of GABA that has been released into the synaptic cleft, if we fix the concentration of GABA in the synaptic cleft, then initially we have a certain fraction of these GABA-A receptors occupied with GABA bound to them. Okay? If we add the Rho 154513, then that will come and bind to the benzodiazepine sites, decrease the affinity of the GABA binding sites for binding GABA, and that will mean that the number of receptors which have GABA bound to them will decrease, basically. So the number of activated open channels will decrease. So the amount of chloride anions you let into the cytoplasm of the cell will decrease. So the inhibitory postsynaptic current you get will decrease. So you're actually going to decrease GABAergic transmission and decrease the inhibition on the postsynaptic neuron, which means that Rho 154513 will be pro-convulsions. It will cause convulsions. Okay, so that's the benzodiazepines then. So we've seen two important examples, diazepam and lorazepam. Diazepam, which is very powerful anxiolytic, and lorazepam, which is very powerful at producing amnesia. And we've seen that, as a rough guide, the reason lorazepam produces amnesia is it favours these sort of GABA-A receptors where the alpha subunit is either alpha-1 or alpha-5, whereas diazepam is good at anxiolytic effects because it favours the GABA-A receptors with the alpha-2 or alpha-3 subunits in them.